Good morning to all. Thank you very much to attend this webinar, this Iberian webinar that I, Gloria Desir, and Adelia Nunes, from Portugal have coordinate. And as you have known in the flyer, the webinar is structured into parts. 4 speaks with a half break and other 3 speaks. And we will start with Davinia Moreno, okay, with his speak entitled On the Potential of Air Dating in Geomorphology. And I will say nothing more. Only thank you for joining us and to participate in this webinar. And Davinia, please, you can start with this webinar. You have
Okay. Okay. So before starting this presentation, I would like to thank the Gloria and Adelia, the coordinators of this webinar, and the International Association of Geomorphology for inviting me to participate. I'm glad to be here today, and I hope you will like this talk. So I'm going to talk about the potential of ESR dating in geology and geomorphology. Electrospin resonance is a powerful technique that is frequently used in chemistry, in physics, biology, but its use for quaternary geology is one of the most original applications. ESR can be used in 2 different purposes. Characterization of ESR signals as an indicator of the sediment provenance, but the most important application is geochronology. Since the first application of ESR for a dating objective in 1975, the quality of ESR spectrometers and the understanding of the structure and behavior of the ESR signal used for dating had been significantly improved, and numerous dating applications have been developed on many different materials, such as carbonates. We can use mollusk cells, speleothems, corals. We can also date silicates, feldspar quartz, silex, and also phosphate teeth, mainly teeth, fossil teeth, and also sulfates, gypsum. That means that many different geological contexts can be dated by ESR, and many different informations can be obtained using this technique. For example, we can determine the neotectonic activity along coastlines using corals and mollusks. We can date whole system of alluvial terraces set up following climate changes and tectonic movements using quartz from sediments. And we can calculate the age of past volcanic eruptions or paleoseismic events using also quartz. And we are also able to establish chronologies for events in human biological and cultural evolution using tooth enamel, speleothems, or even bone flint. I'm sorry. Sorry. So we all know that in quaternary, we can use many different dating methods. So why use ESR dating and not another method? The choice of the dating method depends on the presence or absence of suitable materials for this objective, which is closely related to the geological context and the presumed age of the site. The main advantages of ESR dating are that this is one of the very few dating methods that may be applied to fossil remains beyond the radiocarbon and the uranium Sirius dating time range. We can see that here, the radiocarbon dating and the uranium thorium series is limited to a very short period. And with ESR fossil teeth, we can go farther. It's one of the very few dating methods that can be used for the whole Quaternary period and beyond. We can see here again that with quartz, we can go farther in time than if we compare with other dating methods. And it is one of the very few dating methods that may be applied for dating sediments in non-volcanic context. Furthermore, given the wide range of materials that can be dated using ESR, the method can potentially be used in almost any quaternary environment. This contrasts with most of the numerical dating methods, which are usually limited to a specific context. That's why this technique is increasingly used in archaeological and geological studies. But how does ESR dating work? I imagine that almost everyone here is familiar with luminescence. That's right? Okay, you cannot answer. So similar to the optically stimulated luminescence, ESR is also a paleodosimetric dating method based on the use of geological materials as natural dosimeters. These materials are able to naturally register the total dose of radiation received by the sample during its history. But ESR dating exceeds luminescence in utility due to longer time range and greater variety of suitable sample types. ESR method rests on the principle that the natural radiation produces free electrons which can be trapped. This is the natural radiation. It produces free electrons who can be trapped at the defects in the crystal lattice of minerals. These traps are called paramagnetic centers. The quantity of trapped charge accumulation increases with time and can be quantified by ESR measurements. To make it simple, an age is basically obtained by the determination of these two variables, the equivalent dose, or the total dose absorbed by the sample over time, and the dose rate. This is the mean dose value absorbed by the sample every year. To determine the equivalent dose, we use the additive dose method. It means that several aliquots of the sample are artificially irradiated at different doses. One aliquot, this is in green, one aliquot remains in its natural state, and another aliquot here in black is artificially bleached in the laboratory. And we'll explain later what is bleaching, okay? All these aliquots together are used to obtain this kind of dose response curve that allow us to determine the equivalent dose by extrapolation of this line to the horizontal axis. Here we can see the dose equivalent, or the equivalent dose. The dose rate, it means the dose absorbed by the sample every year, is the sum of the alpha, beta, gamma, and cosmic radiation, this formula. These doses are emitted from the environment and from the material itself. The reconstruction of this dose is highly dependent on different parameters, such as water content in sediments, size grains of quartz, the attenuation of cosmic rays due to latitude, altitude, and overlying sediments, and inhomogeneities or radioactive elements in the sediment. I can say that the calculation of this dose can be really complicated to determine. It's very complicated because we have to take into account many parameters. So the fieldwork is extremely important because during the fieldwork, we are going to obtain most of these parameters. That's why geochronologists will insist to geologists and archaeologists in the fact that we have to go to the field to take samples for ourselves, because otherwise we can lose a lot of information. Among all of materials that can be used for dating, quartz is the most important mineral for dating because of its wide distribution on the Earth's surface and the presence of various paramagnetic ESR centers. ESR dating of quartz is based on the hypothesis of ESR traps zeroing by sunlight during the transport prior to the sediment burial. This is called bleaching. What I mean is the number of electrons, of free electrons, trapped in the paramagnetic centers is equal to 0 at the moment of the sediment is in contact with the sunlight for the last time before its burial. I try to represent this in this figure. Here we have a rock. This rock is eroded. And during the transport of this quartz grain obtained from the erosion of these rocks, for example, these quartz grains can be transported by a river. During this transport, the dose absorbed by the sample when the quartz was part of a rock is released. I mean, here during the when the rock is a part of a mountain, is absorbing radiation and trapping electrons in the paramagnetic centers. When this rock is eroded, the quartz grain are transported by the river, and when these quartz grain are in contact with the sunlight, the electrons are released. So when this sediment is deposited, we assume that the number of electron traps is 0, okay? This releasing of electron is called bleaching. And this is the most important part of this dating technique. So we have to take in mind that the calculated age doesn't correspond to the crystallization, but to the time elapsed since the deposit. Because once the sediment is deposited, the natural radiation starts working again. I mean, the electron start to be trapped again because they are not in contact with the sunlight. Do you understand? Well, if you have any question later, I will try to explain more this part. The quartz have different paramagnetic centers, but their paramagnetic centers showing the best potential to date quaternary sediments are the aluminum center and the titanium center. But there are other centers that could potentially be used, such as the E' center, for example. The aluminum center is the most used in geochronology because it is always here, it is always seen in quartz, but his bleaching is incomplete. Only a part of trapped electrons is released, even after a long time light exposure. So a residual dose must be subtracted from the total dose in order to obtain the dose really received by the sample since its burial. On the contrary, titanium center shows a complete bleaching. ESR age calculation involves, that's I said, many parameters in order to accurately estimate the different components of the dose rate. The number of these components may exceed 20 depending on the characteristics of the sample considered. Each parameter has an associated uncertainty that needs to be included and propagated into the final age calculation, which usually makes a final age error at 1 sigma in the range of 5 to 15%. For this reason, the precision achieved with ESR dating may somewhat contrast with that of other reference dated methods such as argon-argon or radiocarbon or uranium series, which can be less than 1% at 2 sigma. But although the precision achieved is significantly lower than that of the more established methods, ESR dating is in many cases the only numerical method that can simply be used at a given site. So I think I have already talked a lot about the method. So I would like to present some applications that I think is going to be more interesting for you. Okay, so we all know that the geochronology is an essential tool in tectonic geomorphology and paleoseismological studies, because the quantity and quality of the geochronological data used may have significant socioeconomic implications. This paper has been recently published last year, and it's a very huge collaboration work who had two main objectives, which are closely linked to each other. In this paper, we wanted to revisit the slip rate of quaternary faults in the Iberian chain in Spain, but we wanted also to evaluate the validity of the ages provided in the 90s or early 2000s years by a now closed luminescence laboratory located in Madrid. In this case, we use 4 dating methods, and we applied for the first time ESR dating in this area. We analyzed 7 samples of ESR dating, 3 for OSL dating, 3 for uranium series, and 3 for radiocarbon dating. We work in 3 different areas, and we studied 3 different faults: the Munebrega, Daroca, and Concoux-Teruel fault. The new geochronological data that we obtained using mainly ESR dating demonstrated that the slip rates of the quaternary faults in this area are significantly lower than those previously estimated using the old luminescence ages. The lack of consistency of the previous luminescence ages and also the precarious information about the methodology applied by the luminescence laboratory seriously questioned the reliability of the previous ages, which significantly overestimate the activity of the faults, potentially leading to substantial seismic hazard, overestimate with social implication. In this work, ESR dating was a crucial part to get this kind of interpretation and this revisiting of the slip rates of the quaternary faults, because we were able to obtain ages 6 times older than the previous one. And it is very important because in this area it was supposed to, it was I don't know how to say this word. There was an hospital that had to be constructed, and this construction was stopped because of the slip rates of the quaternary faults in this area. And this new paper demonstrates that this hospital can be constructed without any problem because it's not so active, so tectonically active, this area. So let's go to another context in which we can use ESR dating. This is a fluvial terraces system. The Pleistocene fluvial terraces system represent a great interest for both geologists and archaeologists because they have recorded tectonic uplift, climatic variation, and human occupation. That's why this is one of the geomorphological contexts in which ESR dating has been most widely applied in recent years. I have selected some papers from the last 20 years in which ESR dating has been the main method used to establish the chronological framework of a river system. This paper, published in 2004, was published by members of the ESR dating team of the Muséum National d'Histoire Naturelle in Paris. And they presented 46 samples from 2 different rivers. The Ion River system, which is a tributary of the Seine River, and the Cross River, which is a tributary of the Loire River. In this figure, this paper is a little bit old, so the figure is not very good. So you can see how many samples were taken for each terrace of this river, and also for this one, for the Cross River. So we cannot date a system river using only one sample for each terrace, okay? In general, we take many samples and we try to combine all these samples to obtain a precise and accurate age. In this paper, the authors demonstrated the potential of the ESR dating method to elaborate chronostratigraphical frameworks on several Pleistocene fluvial systems in France. But this is one of the first papers using this dating technique for this objective, but it is not the only one. And many other authors have applied ESR dating to other river systems in different countries because of the usefulness of this method in this context. For example, myself, I applied this dating technique in the Arlanzón River, a tributary of the Duero River in Spain, and closely linked with the development of the Atapuerca karst system. For which, who don't know Atapuerca karst system, this is an international, very famous karst system because of the fossil remains that we had found inside the caves of this karst system. This is an UNESCO heritage worldwide site, okay? So the importance of this paper was in 2 ways. So the archaeological sites and the geomorphological point of view. Also in China, in the Minjiang River, this method has used to establish the geochronology of the whole system. And trying to get farther in time, this paper, also published last year, presents the first numerical ages for the uppermost level of the Cenozoic basin field of Western Iberia. This new chronology obtained by ESR dating is very important because in this area, the available numerical dating is quite limited and mainly restricted to the lower level terrace deposits because of the limitation of other dating techniques. Because when you try to date all terraces the number of dating methods that you can use is very reduced, okay, it's very limited. So this is a very, very important work, and it's very appropriate for this Iberian webinar because it's a work from Portugal, but it's very important also for the Spanish Tejo basin. But we have also worked about, we have also done a lot, carry out a lot of work on the methodological development of the technique to improve protocols and obtain more accurate ages. In this paper, efforts were made in order to determine the relationship between the bleaching and the distance covered by a quartz grain in a river, and also an investigation about the different titanium centers and their particularities when calculating the equivalent dose. These works have been very important for ESR dating because now we know that when we start working in another river system, if we know the geological history of the deposits, we can establish if the bleach was completely or not, and we can work with another information. I mean, for us, the bleaching is very important. If we know that the bleaching has not been complete, we need to calculate this residual dose. So if we know the minimal distance transport required for getting a maximum optical bleaching, we can start working with more information. And this other paper, it has been a very important information because now we can use with more accuracy. We can obtain more ages for the same sample, and we can combine these ages to obtain a more accurate data. But we can also work in karstic context. We know that caves contain a variety of deposits. In theory, all these deposits can be used for dating purposes. But the majority of papers about ESR in caves are about dating carbonate from speleothems. For example, this one. But we can also, in archaeological context, date fossil teeth and also sediments, because this is an indirect age, but it's very important also to strata where we don't have fossils. And for the last application to finish, I would like to talk about this paper published by Chinese researchers, because it's very important for the method. For decades, ESR dating has been thought to be limited to the Quaternary period because of the saturation of ESR signals. But in structural and petroleum geology, geologists often need to determine the formation age of pre-Quaternary faults to study tectonic movements in earlier geological periods. In this study, authors try to expand the ESR dating to the pre-Quaternary using samples collected from faults in the Sichuan Basin in China. And their results are consistent with fission track ages and the regional tectonic evolution history. So it seems that ESR dating could be a practical method for dating pre-Quaternary faults in a structural and petroleum geology application. So thank you so much. And if you have any question, I'm here.
Hello, good morning. I'm Domingo Carbonel from Zaragoza. Thank you very much for attending. I would like to present a communication entitled Application of the Trenching Technique to the Investigation of Gravitational Processes. The presentation follows the next structure. First, introduction. Second, methodology. Third, research samples, gravitational faults and sinkholes, and finally, conclusions. The trenching technique allows the study of surface deformation by the analysis of the structural and stratigraphic relationships exposed in artificial excavations and obtaining
Sorry, I'm sorry. Oh, sorry.
The trenching technique allows the study of surface deformation by the analysis of the structural and stratigraphic relationships exposed in artificial excavations and obtaining geochronological information. The trenching technique has been widely used in paraseismological studies to evaluate the seismogenic potential of active faults. However, its application to the investigation of gravitational deformation has been very limited. And practically null in case of structures related to evaporite dissolution. It should be noted that all of the works carried out in this type of structures have been made by our research group. The success of the trenching technique is highly dependent on the correct location of the trench. Because of this, it's essential to carry out detailed geological and geomorphological maps in order to understand the structure distribution. Additionally, some geophysical techniques, such as GPR and electrical resistivity tomography, can be used to precise the location of the trench. Here I have some samples of GPR and electrical resistivity tomography. Trenches should be excavated perpendicular to the investigated structures and be sufficiently long and deep to expose a complete log of the formation. As a following step, after cleaning the walls very good, it's necessary to install an orthogonal grid. This grid serves as a reference for mapping the selected wall. Here have a grid example. After cleaning and grid installation, the structures and stratigraphic units are identified with color pins or spray paint and mapped on a graph paper. Once the trench log is finished, we search and sample datable material. The most common dating techniques used to obtain geochronological data in the trenches are the radiocarbon method and optically stimulated luminescence, OSL. Finally, we carry out a retrodeformation sequence. This consists of recovering the stratigraphic units and structures sequentially and in reverse chronological order, allows obtain parameters on the retrodeformation phenomena, such as the displacement rate or the recurrence of events. The research works in which the trenching technique has been applied to a study of gravitational deformation have been carried out in mass movements, rotational and translational slides, lateral spreading and succun, collapse and sagging sinkholes, and finally in gravitational folds. Next, I will present examples in which we have applied this technique for the study of gravitational folds and sinkholes. These examples belong to works that have been published in different international journals. The research works in which we have applied the trenching technique to the study of the gravitational structures have been carried out in Iberian chain, northern of Spain. Here we have evaluated normal faults related to the interstatal dissolution of the Triassic evaporites in the central sector of the Teruel Neogene Graben, and the Cenzano fault scarp located in the northern edge of Camerus Massif, which constitutes the southern margin of the Ebro Tertiary Basin, and flexural slip faults related to the evaporite dissolution located in the Grand Hotbed monocline, where it forms the western margin of the Carbonel collapse center. Different structures have been recognized in the different trends. For example, half graben, fissures, horst, and colluvial weight. The stratigraphic and structural relationships observed in the trenches provide unexpected evidence of an episodic displacement regime for all of these structures, allowed us to determine the number of displacement events, and we obtained the table material which allowed us to establish the different vertical slip rates, the recurrent faults events, and the most recent event. The measured values are higher than those expected for tectonic faults in the same geological context. In the following slides, I show some examples in which we have applied the trenching technique to evaluate sagging and collapse sinkholes located in urbanizable areas of the Zaragoza city. The study area is located in the central sector of the Ebro-Cenozoic basin. Here, the Ebro Valley has been excavated in the subhorizontal lagging evaporite of the Oligocene Zaragoza Formation. This continental formation, several hundred meters thick, displays secondary gypsum at the surface and thick halite and glauberite units in the subsurface. In the Ebro Valley, the soluble bedrock is extensively covered by terrace deposits, locally thickened due to a sedimentary dissolution. Zaragoza city and its outskirts is most probably the area in Europe where sinkholes hazard related to evaporite dissolution has the highest economic impact. The first example displays a trench excavated in the Miraflores suburb. The trench shows a collapse structure limited by subvertical fault planes. The second example, the trench excavated in the Valdefierro sinkhole, reveals a sagging structure. The outer thorn is affected by small through normal faults and fissures that counterbalance the contraction associated with the downward bedding. The structural and stratigraphic relationships observed in the trenches have allowed us to establish type of subsidence processes, limits of structures, establish setback distances, cumulative vertical displacement, minimum average subsidence rate, recurrence events, and the sinkhole evolution. Finally, I would like to present some conclusions. Detailed geomorphological mapping is an essential task for the correct location of the trenches. Mapping significantly increases the chance of success of the trenches and our ability to interpret them. Trenches make possible to demonstrate that geomorphological anomalies are related to surface deformation and are not the product of other processes such as differential erosion or human activities. The trenches allow to locate the limits of the deformation structures precisely and the areas of the surface susceptible of undergoing significant differential movements. The geometric relationships observed in the trenches allow us to characterize the deformation style and establish its kinematic regime, progressive or episodic. The analysis of the stratigraphic and structural relationships exposed in the trenches, along with the analysis of the retrodeformation sequence, allow us to reconstruct the deformational and sedimentary history associated with the faults and sinkholes. This information, combined with the geochronological data, offers the possibility of characterizing gravitational deformation quantitatively by means of several parameters: displacement rates, chronology of deformation events, especially the most recent event, vertical slip rates, the recurrence event, and its variability. Many thanks for your attention.
So good morning to everyone. First, I would like to thank Gloria for inviting me today in this webinar, where I'm going to talk about the use of drones in coastal geomorphology. As Gloria said, I'm Lara Talavera, and I'm right now a postdoctoral researcher in the University of Faro, in the University of Algarve in Faro, in South Portugal. So first, I'm going to talk a little bit about the coast and the coastal processes that act at different temporal and spatial scales. Then I will be talking a little bit about the methods that we can use to monitor the coastal zone. Next, I will a little bit comment briefly about some fundamentals of drone photogrammetry, and also a little bit about the workflow that one needs to follow when flying drones to obtain topography of the coast or other areas of interest. And I will finish my presentations talking about some drone applications that I have the opportunity to work in, mostly during my PhD that I did in Cádiz, in the University of Cádiz in South Spain. And also works that I'm doing right now. So to start with, some of you may be familiar with the coastal zone. The coastal zone is the interface between three major natural systems, which are the atmosphere, the land, and the ocean. It is an area in which the sediment or material are transferred from the land surface to the ocean systems, and the sediment being eroded by rivers, glaciers, earths, etc., that finally reach the beach and the near shore, and also maybe the ocean floor. So in the coastal zone, there are many physical processes that act at very different temporal and spatial scales. So all of these temporal and spatial scales make the coast to be an extremely dynamic environment. For example, the spatial and temporal scales can go from the instantaneous scale to the macro scale. Examples of some coastal processes acting at the instantaneous scale would be, for example, the formation and disappearance of ripples or mega ripples in the beach. At the event scale, we would see changes in the beach profile or the coastal dunes in the shoreline that result from the impact of storms of different magnitude. The mesoscale relates to the interannual or seasonal variability in the previous coastal dunes or the previous beach or the shoreline. And finally, the macro scale could imply changes in large-scale coastal landforms, such as, for example, barrier islands or sandy spits. The coastal zone has been traditionally monitored using different remote sensing techniques. Of course, these different remote sensing methods offer some disadvantages and advantages for study the coast. So, for example, there are many authors and works done using satellite imagery and aerial photos, and these are good to check decadal changes of for example, the shoreline or dunes, because they cover an extensive land. They cover a large extensive area. But for example, the temporal resolution of these images may not be adequate to, for example, study changes derived from the impact of a single storm. If we want to look to that, we could use some other ground instrumentation, such as real-time kinematic and differential global positioning systems. I'm sure most of you are familiar with these instruments, which I'm pointing here right now. And with this, we can obtain very accurate data of the elevation of the beach, of the changes in elevation, along, for example, several profiles along the beach. And we would have highly precise data as many times as we want to repeat the survey, but we are missing information in between these profiles. But if we are interested in mapping with a lot more dense information and accuracy, we could use also other ground techniques, such as the terrestrial laser scanners, or even we could use a LiDAR. But these techniques are really expensive. So, of course, all of these methods have their disadvantages, and recently many authors have stated that we need high spatiotemporal data to improve our knowledge of short-term coastal processes and understand further the evolution of these systems at the coast. And this is where the drones have an important role, and this is why also the drones have emerged and are a really widely used tool, not only in the coast. The drone technology is a low-cost technology that allows you to work with a certain degree of automation, which makes things easier. It's also characterized by being a very for its versatility, and we can use it to map beach and dune systems simultaneously. And this was not easy before with the previous techniques. For example, if we were using a GPS, we would have to go walking through the dunes, trampling the dunes, trampling the vegetation, etc., to take some distant points, and maybe with those points build a cloud. But with the drone, we are allowed to obtain the whole surface of the dune plus the whole surface of the beach together, and obtain the elevation of that area with a lot of accuracy and as many times as we want. So it is a great tool to obtain high resolution topography of the coast. And how do we obtain high resolution topography of the coast? First, of course, you need a drone that is equipped with a camera. But you need also some specialized softwares to process all the images that are captured by the drone. And these softwares work with what is called structure from motion algorithms. And in my opinion, the drones have become really famous tools, of course, because of this potential they have. But for me, another impressive thing is what these algorithms, structure from motion algorithms, can do in this software. So what the software and these algorithms do is to look for potential common features between a set of highly overlapped pictures that are taken by a drone. And from the 2D information that is contained in those pictures, and also with the information that the drone records along the trajectory, because it records the position and the angle of the camera. So using these common features, these images, and the position and angle of the camera, the software, it is able to reconstruct and triangulate the position of every point that is visible in those many images and obtain its 3D coordinates. So basically what these algorithms do is to reconstruct in 3D, for example, these bits, from the images, the 2D information contained in the images of the beach. And the result, as you see here, is a very dense point cloud. And I'm going to show you an animation for you to see the degree of detail that we can achieve. This is a very high density point cloud of a beach located in Cadiz. This was my study case of my PhD. And this is a 3D model. This is not a picture or a video footage made with the drone. Okay, I'm going to briefly describe the workflow that one needs to follow to obtain topography using drones. So first of all, we need to plan the flight, and for that, first we need to decide what is the pixel size of the images that we want to achieve. What is the resolution that we want to get from the drone images? After that, we will need to choose the flight elevation of the drone. And very importantly, we need to decide and to use a high image overlap between the images. We need to, because as I said before, the software searches in the images for common features between a lot of images. So it is important that these images are highly overlapped for the software to find common features and to improve their reconstruction. So it is important that they use a high front and side overlap during the trajectory that the drone follows. And also some other aspects such as the wind conditions of the day you want to fly, the presence of obstacles in the area such as street lights or whatever. Also, you need to be aware of the permits that you need to fly drones in certain areas. For example, in my PhD, I needed 3 different permits because I was flying in a natural park. And also I was flying close to a military area. So you need to be aware of that. And for example, if you're interested in mapping the lower beach area, you also need to take into account the time of the tides. When is the low tide and when is it going to rise? After that, after planning the flights, we would go to the field and do the flight. But before launching the drone, we will need to deploy what is called ground control points, which are targets that are visible from the drone and are visible in the images. And we need to measure the coordinates of these points, the black squares that you see here, using a GPS. And these ground control points is what is going to orient, scale, and position all the images that you're taking. So the final 3D models that you obtain after the processing are well georeferenced. Also, in the field, it's necessary that you take what is called individual checkpoints. And these checkpoints is what is going to allow you to check the accuracy of your model. Basically, you're going to compare the coordinates of these points that you take with the coordinates of your 3D models and compare how your models differ from the real topography. After that, you fly the drone, record a lot of pictures, and you go to the laboratory where you have your computer and your software, and you do the processing, and you will obtain 3D models from the 2D information contained in the images. And here, these two are two softwares for drone image processing that I've used, just for you to know if you're interested. And what are the outputs that we obtain? Well, we obtain dense 3D point clouds, we obtain digital elevation models, and also orthomosaics of the area of interest. As I said before, on the field, we needed to measure some points to assess the accuracy, the vertical accuracy of our models, but this accuracy is not homogeneous over the study site. For example, in this map, you see the errors found in the different points. And as you see, there are some areas closer to the lower foreshore where the water is that are exhibiting higher errors, and also on the sides. And this is due to the varying visual content of the beach and the dunes. For example, here in this picture, this shows the area of the lower foreshore. And as you see here in this area, for the software and the algorithms, it is very difficult to find common features here that are easily distinguishable from image to image. On the contrary, if you go an area of the foredune, you have much more visual content and different textures, not just this plain texture of the sun. So for the software, the reconstruction is much easier and leading to lower vertical errors in the area. Additional factors that should be taken into account or that could lead to wrong reprojected points and higher vertical errors would be the presence of water, moving water, but we can mask that within the software. Also moving objects such as people or cars in case in your area there's a road or there's traffic. And more importantly is the illumination conditions during the drone flight. If the sunlight is not perpendicular to the ground, is not totally perpendicular to the ground, this may lead to the appearance of shadows in your scene. And in these areas where the shadows are in the models, the reconstruction would be not so good. So you need to take that into account and fly with the appropriate sunlight to avoid this. Finally, I'm going to talk a bit about some drone applications that I had the opportunity to work, mostly on my PhD, and also on the work that I'm doing right now in the University of Algarve. I'm not going to go into much detail describing the study site, but for example, just briefly, this is the Sunday speed focus of my work during my PhD. I was mostly monitoring these two areas over here, monitoring these changes with the impacts of storms. So one of the things that I was doing was flying before and after the storms. So I had a pre-storm digital elevation model and a post-storm digital elevation model of the area after the storm. And with these two DEMs, I was computing DEM-sum difference, which is basically the subtraction of the initial digital elevation model from the post-storm digital elevation model, and shows the areas in which erosion of sediment happens or accretion of sediment happens. So for example, in this DEM of difference, we see that this area here that corresponds to the beach berm was completely, well, not completed, but was significantly eroded by these two low energy storms, sorry, even reaching vertical erosion of 1 meter at some points. But more interestingly, we were able to monitor the changes happening at these washover fans over here. For example, after these storms, in this washover fan here, we could see in the DEM of difference that the sediment was accreting in the backshore and also along the washover channel with more or less 20 centimeters or between 10 and 20 centimeters of deposition. And also, we also saw that there was deposition of sediment in the sides of the washover lobe. Sorry. And we also saw that the flow of water on shore was eroding the washover channel and the dunes present along the channel, leaving some dune scarps of more or less 50 centimeters. I was also able to assess the beach changes happening due to the impact of high energy storms, such as the storm Emma, that actually made landfall in the Gulf of Cadiz exactly 3 years ago. I wanted to show you this video of the post-state of the area after this storm. As you see, there was a significant erosion along the beach. Also, part of the sediment that was eroded went offshore towards the sea, but another part went onshore through overwash. And the overwash was so significant that it was able even to pass over the road and deposit material on the other side. And also, we had some sediment infilling the water channel present here, with a lot of structures that were damaged. So exactly the same as before, we have here the pre-storm state of the area and the post-storm state of the area. The demo difference allow us to measure with a real good accuracy the vertical changes of erosion and accretion of sediment. So we were able to see all this erosion affecting the beach here, with even 1.5 meters of vertical erosion along this area over here. And also the position of sediment on top of the fordune and behind the road in this area. In this one here, we had some really impressive dune scars, and also the enlargements of some of the washover fans present in this area. For example, we also could see the areal changes in these washover fans. For example, these ones in red that are the pre-storms, the pre-storm shape of the washovers and areas. We were able to see that they experience a coalescence process and they become a unique deposit, which is in the blue color. And these ones on the right, they mostly enlarge their areas. In this one in the middle, I think it was even an increase of 200% the initial area they had. And for you to see, for us to have a mosaic of this area with high resolution allow us to really measure with accuracy not only the area of the deposited material, but also all the volumes. And for example, we could see that the vertical erosion that the demo difference was giving us in this area was of 5 meters or something, and it correlates with what we saw in the field. As you can see, this certainly is 4 meters. So we really map changes with high accuracy, and otherwise with other remote sensing methods, we weren't able to do that, or at least not at a reasonable price. And right now, I will just briefly comment the work that I'm doing here in the University of Algarve. I'm working for a project named Illas Barreira. If you want to look to have a look at what we do, I put it here the link to the website. And we're working right now in an island, in one of the barrier islands that are located in the Ria Formosa in South Portugal, which is called Barreta Island. So in this island is formed of extensive gray dunes, which is these gray dunes that you see here, which are fixed coastal dunes with herbaceous vegetation. And what we are doing is to identify, we are monitoring this area using different remote sensing methods, such as satellite imagery, also Google Earth images and drones. And we were able to identify 2 main areas that were showing vegetation disturbance. As you can see clearly in this image, this is one of the areas, this big one, and there's another here on the background. This degradation of the vegetation is attributed to the settlement of 2 ghoul colonies, which breed here and are, as you see, destroying or degrading a lot the present plants and associated, the present plants. So in these 2 degraded areas, what we are doing is to build ghoul exclusion areas, and we're going to see if by excluding the access and trampling of gulls to certain areas, the vegetation is going to actually recover or not. This is an ongoing project. We don't have all the research yet. And this may not be related with geomorphology, but in fact it is, because if this ghoul pressure continues, it may lead to possible changes in the dune sedimentology, because if the vegetation disappears, the sediment would be free, let's say, to to be transported by the winds. And this could change the dune state from fixed to mobile in the very long term. And also we were able to see some gullies that were that were appearing on the area after intense rain events, and we're also mapping those and see how this is affecting the future trajectory of the dune. And that's all for me. If you have any questions, I'd be happy to answer. Thank you so much.
Okay, well, first of all, thank you very much, Gloria, to invite me to speak today here. I'm really happy to be here with you. Yes, as Gloria has said, I'm Nacho Zapico. I am a postdoctoral researcher with a Torres Quevedo grant in the company Diseño y Desarrollo Minero, and I also work as a researcher in the Complutense University. And today I'm here to speak to you about a new discipline, geomorphic restoration or reclamation. I will start speaking about the problem of the impacts of the human Earth movement activities and how traditional engineering practices try to deal with this problem. Next, I will describe what geomorphic reclamation or restoration is, with some examples here in Spain. And I will end my talk with speaking about some of the monitoring techniques that we use in our projects, just in case it would be interesting for you. The first thing that we have to take into account is that human beings nowadays, we clearly depend on Earth movement activities such as mining or civil engineering projects to our day-to-day life. Our screens, mobiles, tablets, computers, almost everything are done with minerals that we extract from mines, as this that you can see on the screen. And as a consequence of these activities, we modify, and in many cases, we destroy all the components of the landscapes. We destroy the shapes, the landforms, the soils, the vegetation, animals, and so on. What it is called on-site effect. However, human Earth movement activities not only modify the affected landscape, we also with these activities we also modify and in many cases destroy downstream landscapes. Normally they are associated with spillages that degrade fluvial downstream ecosystem. Now in the presentation you can see an example of the Alto Tajo Natural Park here in Spain, where the Tajo River is taking spillages from abandoned mines restored with traditional methods. Those activities, human Earth movement activities, mining or civil engineering projects, also destroyed the key element in fluvial landscape, the drainage network. It is really important because a drainage network is what manages water and sediment erosion and stabilize the landscape. Well, traditionally, engineering practices try to avoid those impacts, on-site and off-site effects, by trying to restore the affected landscapes with a smooth, long and steep surface, slopes called terraces, without any drainage network at all. Well, as a result, this lack of a drainage network enables real and gully processes. It is a consequence that the landscape try to reestablish this drainage network. But the problem is that these erosive processes prevent the landscape to redo a healthy new ecosystem. And real and gully processes are really severe. Many reclamation in terraces can evolve to a badland landscape. when they are very severe. It also happens in some abandoned mines in the Alto Tajo Natural Park. I always refer to the Alto Tajo Natural Park, the mining area of the Alto Tajo Natural Park, because almost all my research are conducted in this landscape. Well, in this context, it seems clear that we cannot plan a reclamation project in a degraded landscape without introducing a drainage network, without properly managing water and sediment erosion. And it is what geomorphic reclamation tried to do. The first aim of geomorphic reclamation is try to design and create new stable landscapes based on natural shapes, such as drainage channel networks and hill slopes. And it is applied in landscapes that have suffered the earth movement activity. Well, geomorphic reclamation as a term is not something new. It has been discussed by many authors several years ago. However, the use in real projects, it is the use of geomorphic reclamation in engineering projects. It is new because now we can do that project. Why? Because now we have software packages that let us to design such complex 3D landforms based on natural shapes. For instance, with those softwares, we can design full catchments elements such as a complex 3D drainage network. The channels of this drainage network have concave profiles, as the natural channels do. The transversal profiles also of those channels also have boundful and flat plains sections. Boundful and flat plane sections also vary along the channel. And for instance, other elements, other geomorphic elements and processes that we can design and construct with those methodologies are complex rounded hills between the channels with convex and concave profiles. Well, now on the screen you can see one of these designs. It is a watershed with all those elements, channels, rounded hills, and all the landscape is connected with the natural surrounded landscape with a local base level with the same slope, height. This is the point. With those designs, we try to copy what the natural would do over the time and to connect all the landscape with natural shapes. Well, the next step when we have done a design is to construct it in the field. One important thing is that we don't use any special element. The key component of this methodology is how do you manage the earth. Now, and to do that, we use the same machines that we have in any mine or engineering project around the world. We use a bulldozer, an excavator, and articulated trucks. For instance, now on the screen you are watching how the machine is opening one main channel. This is the main channel design, and the machines are constructing it. And in this other view, you can see how a bulldozer is shaping rounded hills. Well, this discipline is being developed mainly in 3 countries: in the United States, in Australia, and also in Spain. Here we have dozens of examples along all the countries. Some of them have been designed and built in the field, and others just have been designed and we are waiting to the final construction. Many examples exist in the USA, in Australia, here in Spain, but today I am only speaking to you just about 3 because of the time. Then after my talk, I will pass on the chat our website, just in case you can check other examples or whatever. And I also provide you some videos that we have on YouTube to explain more in detail of this discipline, examples, and so on. Well, the first geomorphic reclamation that we did in Spain was in a sand quarry in the village of Somolinos. It is located in Guadalajara. Here, a sand quarry was restored with traditional methods, with terraces. And these terraces experiences a severe gully and real erosion, as you can see. Then the local authorities asked us for a geomorphic design to try to stabilize the landscape. We did the design, you can see here. And after, in 2011, we started the construction. Here you can see the first hectare that we restored with this methodology. Again, you can see the channels, rounded hills. This is the base level which we connected the first hectare. And now you can see a view of the reclaimed area nowadays. In the upper pictures, again, you can see the restoration, the degraded area prior the geomorphic reclamation. And in the bottom pictures, you can see the reclamation nowadays. We have monitored this reclamation during 10 years, and the final results will be published in a journal this year. But I can say now that the reclamation is totally stable. It is producing sediment yields very low, similar to the surrounded natural landscapes. And also, a high biodiversity landscape is being developed nowadays, as you can see here. Well, the next project that we built in Spain was in the active mine of the El Machorro, also in Guadalajara. This project was really important. It was the first project that we built in an active mine. In this case, the owner of the mines, Caubar Company, a company of Caurín, decided to adopt this method, geomorphic reclamation, for some areas of their mines. We started the reclamation also in 2011, and you can see here when we started the project to reclaim those areas. And it was the reclamation after the project, the first step of the project. This monitoring, this project was restored in 2011, and we have also monitored until 2017. This monitoring also show how this geomorphic reclamation is being stable nowadays, producing low sediment yields and also similar to the surrounding natural landscapes. And also now it is supporting a high biodiversity. All the results of this project and the methodology followed in the construction and also in the monitoring has been published in 2018 in the journal Ecological Engineering. Well, this case, the Machorro case, and the paper published in Ecological Engineering was used by the European Union to recognize geomorphic reclamation or rehabilitation as one of the best available techniques for the management of waste from extractive industries. It means that the European Union recommend to any company that has waste material in their activity to restore with this method, to stabilize the landscape and be able to support a future healthy ecosystem. Well, and the last example that I am going to show you is in the abandoned Nuria mine, also in Guadalajara. In this case, we use and apply geomorphic restoration not to restore an affected area, if not to stabilize a rotational landslide. here in this mine, there was a waste dam restored in terraces. You can see here the terrace. And it experienced a heavy rotational landslide that advanced several centimeters a year. So instead of trying to stop those landslides as commonly is done with a concrete dam, with pipes and whatever, we decided to construct two natural catchments around the core of the landslide to stop the landslide. With these two natural catchments, we wanted to drain the landslide, to drain the surface water and the groundwater. And this reclamation was done in 2014, and after 6 years of the stabilization project using geomorphic restoration, the quarry of the landslide keeps being without any movement. All those results have been published in engineering geology. The design of the stabilization project and the monitoring that we have conducted to study the landslide, and also to monitor if the landslide was stable after our geomorphic reclamation project. Well, as you can see, the geomorphic reclamation projects constructed in the field are really new, and they have a really short story. So we need to conduct detailed monitoring research projects to study, to know the extent of the success of this reclamation, or if any problem arises. So we have to conduct several monitoring topographic projects in those reclamation areas, mainly with topography tools. We started to work with laser scans. However, as Lara told us in the previous talk, now we are starting to use status from motion methodology combined with SFM status from motion methodology combined with drone pictures, because we also discovered that this survey method offers better results than terrestrial laser scans. Mining areas are really complex, and in many cases they have high reliefs. So with structure from motion and drone pictures, we get better results in terms of accuracy and resolution. We not only conduct structure from motion surveys to get topography and do analysis of stability. We also conduct structure from motion surveys to research about the best way to conduct those surveys. As I have told you, mining areas have a really complex topography, and traditional structure from motion workflows and drone pattern flights not always offer the best results to work in a mining area. For instance, in cases where we need to know to detect discontinuities to plan our reclamation projects, with those traditional workflows don't offer a good details. So for this reason, we try to know how to use those technologies, structure from motion and pictures from the drone, to get a better result in terms of accuracy and resolution, to get a better to be able to conduct a better analysis to stabilize the landscapes, and how to restore, and where we have to restore some parts of the mine. Well, and the last technique that I want to show you, and that we use in our reclaimed projects, are hydrological and sedimentary stations combined with online and real-time application. With these stations and an online application, we are able to get accurate, reliable, and high temporal resolution results about instantaneous sediment yields to know if a reclamation is working properly or if any problem exists. The workflow that manages the data taken from the sensors and how these data are processed has been also patented, and we are able to get to know and we use this station in both in reclaimed area to know if it is working properly, and also in active mine in case that they can be producing any pollution event related with sediment and water. Well, with this slide, I finish my talk. Thank you very much. And if someone wants to ask something, I'm here. Thank you.
So in this presentation, I will talk about the application of a dynamic modeling to identify buildings at risk and pedestrian travel times to safety areas in a debris flow worst case scenario. So this presentation has two components, the definition or the implementation of the debris flow dynamic simulation, and afterwards the use of this dynamic simulation to identify the buildings at risk and the pedestrian travel times to safety areas. So the study area, it's the Zezer Valley, is located in the highest mountain massif in Portugal mainland. The climate is Mediterranean with warm and dry summers. The wet season extends from October to May with a mean annual precipitation of about 2,500 millimeters in the summit. And snowfall also can occur during the winter, although less frequently than rainfall. In both sides of the valley, the slopes have angles, about 25% of the slopes have angles between 25 and 35 degrees, and 14% higher than 35 degrees. The geology is mainly granitic, and a characteristic of this area is that almost 44% of the basin was affected by a huge wildfire during the summer of 2005. In the left figure, this wildfire perimeter is marked in green. Okay, and these unprotected slopes were strongly affected by debris flows activity during the following rainy season. So at this time, a total of 34 debris flows occurred and were mapped here in the left figure also in black. Okay, although no victims were recorded, these debris flows forced the closing of the national highway in the sector that links the main village to the most touristic places in the mountain. So this was not the first time that a similar event occurred in this region. In fact, the first reports on the occurrence of debris flows in Zezer Valley and also on Manteiga's village date back to the 19th century. In a particular event in 1804, 2,000 lives were lost, 20 lives were lost. And this one happened in this stream marked in green, the village stream. One of the latest debris flows events, which happened before the one in 2005, was reported in 1993 and took place in an area affected by a wildfire 2 years before. Fortunately, no casualties were documented, although a touristic facility was severely affected by the impact and the deposition of debris, and this caused very high material losses. And this one happened in the stream marked in pink. All these remaining streams showed in this figure were also affected by debris flow activity in the past. But we think that these events are underestimated, especially along the Cesar Valley, due to the smaller number of elements at risk. However, there is a lack of information about these events. And even for the latest ones, namely the 2005, there is no record on the volume of the deposited material or even the total amount of rainfall, although we know it happened after a severe rainstorm. So in addition, the field surveying only took place 6 years after the event, which means that the debris flows inventory, this one marked in black, was mainly constructed using an orthophoto map taken 1 year after the event. So to implement the runout simulation, we used a 2-dimensional one-phase continuum model that integrates surface runoff, concentrated erosion in the channels, the propagation, and also the deposition of the flow material. And we back calculated the excess rainfall involved and the rheologic parameters. We only, despite the triggering of the 34 debris flows during the rainstorm in 2005, we only did the back calculation for 2 debris flows because they stood out as the most relevant debris flows occurred during the event, either by the size and volume of the mobilized material or by the conservation of the deposits at the time of the field surveying. The rheological and entrainment parameters obtained for the most accurate simulations were afterwards used to perform different scenarios of debris flows at the basin scale. Afterwards, we used this dynamic model to identify the buildings at risk, as well as the safe public spots, according to the results of the modeling, of course. We applied a decimetric distribution to calculate the potentially exposed population. And we also estimated time lapse between the debris flow initiation and the arrival at each one of the buildings at risk, which of course reflects the time needed to evacuate. The estimation of the time needed to the evacuees reach the safe public spots previously defined was considering different walking speeds according to the age of the population. So for the dynamic modeling, this slide shows the model inputs. We used a digital elevation model with a resolution of 5 meters. And the map of the soil thickness that was based on the simplified geomorphologically indexed soil thickness model produced by Filippo Catani et al. This model was validated by the comparison of the results with 38 field point measures and resulted in a mean absolute error of 29 centimeters. This slide shows the constant and the calibrated parameters used in the model. Concerning the calibrated parameters, we had to choose those that best fit or represent the characteristics of the event. Regarding the rainfall duration, for instance, we don't have any information about the duration or the total amount of rainfall occurred in the mountain, where these debris flows were triggered. However, the 3 nearby rain gauge stations registered a 2-hour period with the highest values of rainfall. Although these 3 stations are located at distinct topographic positions and at distance of several kilometers from the place where the debris flows occurred, we consider this 2-hour period since we don't have more precise information. Regarding the excess rainfall and due to the uncertainty regarding the amount of rainfall occurred, as well as the lack of information about the soils in the catchments, we choose to calibrate the models based on the excess rainfall values. So we found out that excess rainfall values lower than 28 millimeters per hour does not generate debris flows. Thus, the calibration was performed using an amplitude of 1 millimeter per hour. The cohesion, the range of values selected to represent the cohesion, the viscosity, the turbulent coefficient, the apparent friction angle, and also the erosion coefficient were estimated by back analysis. So a total amount of 150 models were computed for each debris flows. And also due to the lack of information for validation purposes, we decided that the outputs from the modeling could be considered valid if they positively answered all the following criteria. The first criteria was the spatial agreement between the simulation and the real pattern of the debris flows. Here we have the two debris flows that were subject of back analysis. Then the simulation must mimic the deposition of the material that have decimetric thickness along the debris flow transport zone. And the third criteria is that the thickness of the deposits in the accumulation area must not exceed 3.5 meters, and the mean value must be between 1.5 meters and 2 meters, because this was what we saw during the field surveying. Regarding the calibration results, for the two debris flows, we found out that values above 30 millimeters per hour are required for sediment mobilization. So values less than 30 millimeters per hour does not mobilize sediments. And for instance, debris flow number 1 requires an excess rainfall of 32 millimeters to allow the calibration of the other parameters, namely the rheology and the erosion factor. And debris flow number 2 requires an excess rainfall of 33 millimeters to allow the calibration also of these parameters. The models computed with the Coulomb resistance and the Voelmi turbulent resistance were excluded because the simulations were not able to represent the deposition along the debris flow track, which was one of the validation's criteria. And the simulations performed with the Bingham and Coulomb viscous models do not present the above mentioned limitation. However, just only one simulation with the Bingham and 11 simulations with the Coulomb viscous model had positive responses to the other two validation criteria, the specific thickness in the accumulation area and the spatial agreement between the simulations and the real patterns of the debris flows. So this image shows the temporal evolution of the deposited material thickness, considering an example of simulation whose results were in agreement with the predefined criteria. The mean values of excess rainfall, erosion factor, and rheology obtained for the most accurate simulation, that were 12, were then used to compute different scenarios of debris flows at the basin scale. We are aware that these parameters most probably vary over the basin. Thus, the creation of scenarios aims to address questions such as what would be the response of the basin if a certain value of excess rainfall occurred, considering the rheology and the erosion factor that best reproduced the runout of the two major debris flows triggered during the 2005 event. So to answer these kind of questions, we developed 3 scenarios, the A, B, and C, with excess rainfall values of 30, 35, and 40 millimeters per hour, respectively. It's not, okay. So here we have the results for scenario A, where no streams previously affected by past debris flows are represented by this scenario. So here in the right figure, we have the streams affected by the historical debris flows, and no streams were affected in this scenario. But 5 of the, out of the 34 debris flows triggered in 2005 were correctly simulated. Here we have the results from the scenario B, where we used an excess rainfall of 35 millimeters per hour. And with this scenario, all the 35 debris flows triggered in 2005 were perfectly reproduced. And as we can see by looking at these two images, we can also see that the scenario is able to simulate the material deposition in 4 streams with historical debris flow activity. The scenario C is considered the worst case scenario, which is able to simulate the material deposition in all the 6 streams previously affected by debris flows in the past, and also the 34 debris flows triggered in 2005. So we used this runout model that allow us to achieve the flow's velocity and the thickness of the deposits to identify the buildings at risk and the pedestrian travel times to safety areas. So we identified the debris flow initiation and deposition, also estimated the mean velocity of debris flows, and estimated the Euclidean distance between the debris flow initiation and each shell of the study area. And these results were lapped with the built area in 2013. So by this overlapping, we were able to define the hazardous area, the safe areas, and the buildings at risk. And of course, the time lapse between the debris flow arrival and the debris flow initiation and arrival to each one of these areas. Okay, so using these 3 areas, we identified the safe public buildings that can accommodate the evacuees, and we proceed to a decimetric distribution to estimate the exposed population. And this decimetric distribution was based on the spatial distribution of buildings, the number of households per building, and the resident population. Then we applied a software, the pedestrian evacuation analyst software, that has an isotropic approach based on the least cost distance. And so we were able to perform evacuation travel time scenarios based on different walking speeds. And we considered 3 different walking speeds: the moderate velocity to accommodate the residents between 14 and 65 years old, the slow velocity to accommodate the residents with more than 65 years old, and the very slow velocity or impaired velocity to accommodate the very young people or with the people with disabilities. The results gave us or delivered us 263 buildings at risk, which we divided in buildings A. We have 96 buildings A, where the debris flow deposition is higher than ½ a meter. So we consider these buildings for evacuation purposes. The buildings B, the buildings categorized or named as buildings B, they accounted for 167 buildings and have debris flows deposition less than ½ a meter. So we consider these unsafe areas, not object to evacuation purposes, but that must be further considered in detailed analysis. 71% of buildings A are affected by debris flows with velocities up to 1 meter per second, and 4% of buildings A are affected by debris flow velocities higher than 3 meters per second. In this slide, we have the identification of secure public buildings. So in the southern sector of the study area, the A figure, the only public building corresponds to a hotel that was severely affected by a debris flow in 1993. And according to our debris flow runout simulation through the dynamic modeling, this hotel is also one of the buildings at risk. In figure B, in the Manteigas village, we identified 3 safe public buildings that have the capacity to house a high number of persons in the evacuation. The decimetric distribution to estimate the exposed population showed us that the total age group of the people, or the highest number of people, corresponds to the age group between 20 and 64 years. But the most exposed population to debris flows are the one with more than 65 years. So in the study area, we have 389 buildings, and these buildings, and 96 of these buildings are affected by debris flows, which corresponds to 113 households and a total residents of 263. 35% of these residents have that are affected by debris flows have between 20 and 64 years, and 56% have more than 64 years. So we performed the pedestrian evacuation scenarios considering different walking speeds, the moderate walking, the slow walking, and the very slow or impaired walking. And we found out that the debris flows take an average of 20 minutes to reach the buildings at risk, with a maximum of 38 minutes and a minimum of 2 minutes. The evacuation time is longer. I'm sorry. So the evacuation time is longer than the arrival time for 18% of the buildings if we consider a moderate velocity, but these buildings increase to 23% if we consider a slow velocity, or even 27% if we consider the very slow velocity. In this slide, we represented the buildings with an evacuation time longer or shorter than the arrival of the debris flows. So in the left figure, we have the evacuation times that exceed the debris flows arrival, and the residents of these 3 buildings require between 45 and 82 minutes to walk to the nearest safe public building. And in the figure on the right, we have the evacuation times that fall behind the debris flows arrival in green or yellow. So for our final considerations, the model used in this study enables the debris flow simulation considering the initiation process by runoff erosion, flow propagation, and the deposition of the travel material. So this is a model that is suitable to represent or to simulate debris flows whose main initiation mechanism is due to the runoff erosion, which frequently happens in recently burned areas. This dynamic model also has the advantage that allows the simulation of the volume increase due to the material entrainment. And the outputs allow the calculation of flow velocity, thickness of the deposits, volume, and extent of travel materials at the basin scale, which are critical parameters for hazard and risk assessment studies. So using this model, we could identify the buildings at risk, but we advise that these buildings must be checked on a case-by-case basis, because it is essential to know the needs or the difficulties of residents for the evacuation situations, and in order to define specific strategies. For instance, we have to know the mobility problems of the residents, if we have bedridden persons, and so on. In situations where the evacuation time exceeds the time of the arrival of debris flows, it is suggested to define new safe public places. In case that this is not possible, alternatively, we must assess the structural capacity of buildings to ensure the vertical safe evacuation. This study has a drawback that related with that only permanent residents are considered in the decimetric distribution. So in case of the tourist facilities, it is advisable to know their total capacity beforehand, as well as the average number of tourists per season. For instance, during the winter or the snow tourism season. The software used, the pedestrian evacuation analysis, proved to be a suitable tool for evacuation studies in mountain regions, since it incorporates the land cover, obstacles that might be in the study area, and also the slope conditions to simulate the travel also outside the road network. And this model also has the advantage to consider the slope directionality, which means that walking uphill will always be slower than walking downhill. And thank you very much.
Okay, I will start by thank you, Adélia and Gloria, for the invitation to make this presentation. I would like to thanks also the International Association of Geomorphologists for organizing this webinar. And my presentation will be about the changes in landscape and landforms promoted by fires, considering its relation with soil erosion. As we know, landscape evolution is promoted mainly by the combined action of endogenic and exogenic processes. Among the exogenic processes, we can highlight the erosion processes, which are extremely important in landform evolution, and especially the erosion promoted by water. Soil erosion by water is a topic under research for a long time. During all the 20th century, it was a topic discussed by researchers. However, soil erosion by water occurred in burnt areas is a recent topic, and it has been developed mainly in the last 30 years. Well, just some 2 or 3 notes related with soil erosion. Well, it is a process of detachment, transport, and deposition of soil components. Just a little minute. We can identify, or researchers in general identify 2 different types of erosion: natural erosion, when it results from the action of only natural factors. Usually this process is compensated by the formation of new soil when there is a dynamic balance between climate, relief, vegetation, soil. And there is the accelerated erosion, also called anthropic or erosion, and it results from the action, the intervention of human with its activities in the land surface. First, this accelerated erosion implies that we have a velocity of erosion that greatly exceeds the soil regeneration capacity. Soil erosion occurs in almost all land surface, and it is an important factor of landform and landscape evolution. When we talk about soil erosion, we have firstly to talk about these processes occurring in areas that are affected by human activities or affected even by fires, forest fires or wildland fires. And this factor, the occurrence of fires, it's one main environmental disturbance that contributes greatly for the increase of soil erosion. We can highlight the different impacts that wildfires promote in soil, water, vegetation, and even in socioeconomic activities, as you can see in this slide. And we can highlight the ones specifically related with soil, increase in runoff and overland flow, increase in soil losses, water erosion, the development of mass movements, gullies, etc. As we can see in this slide, the distribution of fires in the earth is very wide. We can see that almost all biomes are affected by forest fires, and Mediterranean areas are one of the areas that are most affected by fires. As we are here in the Iberian Peninsula, we can see that a great part of the Iberian Peninsula is affected by fires, and even the highest level of fire influence here in the northern northwestern part of Portugal and even Spain. Here's some examples of the satellite imagery showing us the areas affected by different fires in different countries, namely Portugal, Greece, in the European Mediterranean area, but also in the United States, California, for instance, or Taiwan, and even in Siberia. As we can conclude, the European and southwestern European regions are mostly affected by this problem, and consequently, with wildland fires, soil erosion, it's intense, significant factor that is going to occur. In Portugal, we have assisted since the late 70s an increment in forest fires, occurrences, and burned areas, and we even have assisted to an increase in frequency and dimension of forest fires. They start to be the great forest fires start to achieve areas of 10,000 hectares, and nowadays we can observe forest fires that burned for almost 40,000 hectares. Well, but considering soil erosion and the effects it has on landscape and landforms, in the Mediterranean areas, we can say that the soil erosion is closely related with the rainfall regimes. The intensity, the frequency of rainfall, it's a very important factor. Also, the changes in land use and land cover have also an important influence on soil erosion, as well as soil characteristics. Of course, the occurrence of heavy, often localized precipitation can be a significant factor of soil erosion and landscape change, because it causes severe erosion, specifically in areas affected by forest fires, increasing inclusively the risk of flash flooding and debris flow. Considering the erosion promoted by rain, erosivity, there are three main factors that that influence this action: its intensity, its duration, its frequency. These three factors, they contribute significantly for the production of runoff, and this runoff is set off mainly when the precipitation intensity exceeds soil infiltration capacity and when the superficial storage capacity is complete. Well, which are the main influence of forest fires in soil erosion? The major influence is, of course, the removal of the protective coverage provided by the vegetation. When forest fires occur, the first impact is, of course, the burn of the vegetation, which is the protective skin of the earth. Consequently, we observe an increase in rain splash effect. We assist to reducing infiltration and an increase in overland flow and runoff. In general terms, we have a considerable change in the hydrological process, promoting the increased vulnerability of the landscape to major flooding and erosion. One aspect that is very important is that burned catchments not only observe an increase in hydrological risk, but they respond faster to rainfall than unburned catchments. Having an increased runoff, we will assist, or we can assist, to a lower amount of precipitation needed to cause a flood event, and we may also assist to an exacerbation of the impact of precipitation. If we combine this with steep slopes, of course, the potential for flash floods, sorry, it's greater. Well, just some values to compare here the rates of erosion in natural areas or areas affected by forest fires. In general terms, we can say that the rates of erosion, the natural rates of erosion, vary from 0.01 to 15 tons per hectare. Of course, this rate of erosion increases with increasing annual precipitation, considering that soil erosion may be in function of the quantity of precipitation, but also this erosion is also promoted by the difference or can vary considering the variation of plant coverage or vegetation coverage, and that can be very influential in the occurrence of the erosion. In this chart here, we can see that even in areas affected by forest fires, the erosion is more severe in areas where we don't have vegetation coverage, even with burned materials, or where the water repellency is more significant owing to forest fires. In burnt areas, we have some values that show us the erosion rates. For instance, well, I have here some values for areas unburned but affected by anthropogenic action. For instance, areas where there were a mechanical site preparation, we can assist to erosion rates of 15 tons per hectare per year. In agricultural areas, this can reach the 500, more than 500 tons per hectare per year, or in road construction sites, more than 100 tons per hectare per year. In areas affected by fires, sediment yields can range from 0.1 ton to 15 tons per hectare per year in areas where there were prescribed burns. And in areas affected by low severity wildfire, this can goes to more than 300 tons per year in high severity wildfires on steep slopes. Consequently, we can conclude that fire-related sediment yields vary considerably depending on different factors such as fire frequency, but also climate, vegetation, and geomorphic factors. One factor that is important, one note that is important, is that much of the sediment loss can occur in the first year after wildfires, where erosion rates are higher, and factors that influence soil erosion in areas affected by fires are mainly recurrence interval, fire size, and burn severity. Here we have some of the methodologies used to monitor soil erosion. I will just show it, and also some methodologies to evaluate the soil loss. Examples of geomorphic effects of soil erosion in areas affected by forest fires. I have here just two examples in different areas, and in the end I will show you a case here in northern Portugal. Here we have some effects of rainstorms in Northern American area affected by fire. Here high turbidity flood flow after the short fire and real formation, and here erosion gully with a huge dimension, also in the United States. Also here in Portugal, Professor Luciano Lourenço showed us some interesting effects in an area in central Portugal affected by forest fires, and followed by a high intensity rainstorm. Here we have some images that are the testimony of this high intensity erosion with a huge quantity of sediments transport and deposit in the water courses, and the generalized slope erosion. In the Portugal, we assist in the year of 2017 a significant big forest fire near the city of Braga, and here that was sadly known for the intensity of forest fires and the consequences, mainly in terms of human mortality. The case of the city of Braga and its forest fire occurring in October, it's also very well known. It occurred in a wildland urban interface area, affecting 1,000 hectares. As you can see, the destruction was more or less generalized and with different grades of severity. Let me show you in this map. The grade of severity of the fire was differently distributed in the area, in the total area, but there are a high percentage of area affected by high intensity severity. An area with steep slopes. After the 2017 forest fires, we were affected by Storm Anna in December 2017, and it brought us intensive rainfall. As you can see, in less than 12 hours, we have an amount of precipitation of about 100 millimeters. And watching this corner, the hourly distribution of precipitations, we can see here the concentration in about 6-7 hours of intense rainfall, reaching almost 14 millimeters per hour. These have consequent effect on runoff with a high concentration of runoff, and the effects were immediately visible. Here we have an image of the runoff promoted in an area affected by fire, in the Braga fire, and some consequences of the runoff. Well, here there was a small video, but I will pass it. I think I don't have enough time. About the effects of this rainstorm event in burnt areas, we can watch different kind of geomorphic effects. Most part of it was sheet erosion and real erosion, as we have here in the left corner and in the center. Nevertheless, we observed a significant number of gullies, some of them developed in trails, reaching more than 1.4 meters deep and with variable width. Here we can observe one of these gullies in weathered granitic rocks, but also we observed it in other parts of the area affected, gullies with more than 1.5 meters deep, variable width, and affecting weather metamorphic rocks, as you can see here in these images. Some more image here, the right corner, and the consequent impacts on the human infrastructures down in the valley, with destruction of some infrastructures, sedimentation in agricultural fields and in the roads and transportation routes. This map highlights the points where there was a significant interference of where we assist at flash floods and huge sedimentation along the agricultural fields and roads. Okay, sorry. And just for concluding, we can say that wildfire is an important and sometimes most important driving force behind landscape change and degradation in Mediterranean region and also in the rest of the world. Wildfire can have profound effects on the watershed. Burn catchments are at increased hydrological risk and respond faster to rainfall than unburned catchments. flooding and soil erosion also represent some of the most significant off-site impacts of wildfires, because it caused serious damage to public infrastructures and private property, and promotes increased psychological stress for the affected population. In terms of hydrological response of watershed, there is a huge modification promoted by wildfires. Post-fire debris flows are generally triggered by one of two processes: surface erosion caused by rainfall runoff, or landslide caused by the infiltration or rainfall into the ground. The runoff-dominated processes are by far the most common, since fires usually reduce the infiltration capacity of soils, which increase runoff erosion. In this study area, we observed high-intensity rainfall events generalized sheet erosion and real erosion on these unprotected slopes, these burnt areas. We observed also high-intensity rainfall events that were determinant for the development of development and increase of gully erosion, and sediment. Significant volume of sediments were transported down slope, producing infrastructure damage and use sedimentation in agricultural fields. We also observed some shallow landslide. And that's all. Thank you for your attention.
Okay. Good afternoon to all. It's a pleasure to share our research with all the audience. I'm going to present the research that we are doing in Cabo Verde Islands, and our research till now is dedicated to the application of geomorphic index, landform analysis, and dating. Well, Cabo Verde Archipelago is formed by 10 main islands of volcanic origin. Their age formation came since Miocene to present day, and they have an active volcano at Fogo Island. They are tropical islands close to Africa and influenced by Sahara deserts. Their climate is very dry, with some contrast between islands, but at the same time, due to their Atlantic location, they are at the starting point of some hurricanes. We are studying these two weathermost islands, Sant Antão and São Vicente. These two islands have significant geological, geomorphological, and climate conditions and difference. Sant Antão is geologically more recent, has a higher and irregular and less eroded relief, and shows big contrast of annual precipitation between the two flanks of the island. Both were affected by flank collapse of the volcanic edifice, as we can see clearly on the submarine floor around Sant Antão Island. From a general point of view and from exometry, and comparing with other islands, we can see that these two islands are very distinct. Sant Antão shows a relief with a low erosion stage. We can see in the hypsometric curves that Sant Antão is this one. Meanwhile, São Vicente is a high erosion stage, where significant parts of the volcanic edifice have been eroded, like we can see in this perspective. This is Sant Antão and this is São Vicente. One of the most interesting and abundant landforms of these two islands are the isolated or coalescent alluvial fans that we can see in this slide. These fans were our first geomorphological targets and responsible for our subsequent visits. Last year, we published a paper about the alluvial fans morphometics of Savicient, where we get measures of 238 alluvial fans, quantifying fan and catchment morphologic properties, such as gradient, relief, and length. The statistical analysis combined with the morphological analysis allow us to understand the distribution of fans in the island and relate the type of fans, their presence or absence with even different relief sets around the island, as we can see in this general schematic below. Nowadays, we are studying the longitudinal alluvial fan channel profiles and the drainage divide mobility. The preliminary results show that most of the profiles are close to steady state, as we can see in this one. And related with drainage mobility, it seems that we have a dominant situation of stability. However, we have three areas where inland drainage seems to be victim. These three areas that are here. We think that this situation can be related with sea level variations with the distance from the coast and bedrock resistance. The other topic that we are developing is the landform analysis and dating of these alluvial fans, especially the big ones like these two. I'm going to present the results that we already have for the Pedrinha complex of fans in Sant Antão, this one. And this fan has 6 kilometers of length and a huge catchment inland, this one, which could be linked with an old volcanic crater. As we see in this photo, the pile of sediments is not exclusively of the fan, and we can find inside the catchment till the apex 10 meters of infill. Most part of the year, we don't have water on the active channel, that we can see here, but the rainy events normally produce huge and rapid hyperconcentrated flows. This is the perspective from the fan, and we can see a perspective of the mean fan surface with a bar and channel topography. Here we can see the distal fan surface that is already eroded by sea with a low relief surface and some channels already inset in the surface. And here we have a perspective of the distal fan, where we have a modern active lobe, and that shows that fan is active and prograding to sea. In the fan, we can find incised channels. This is the main incised channel that we have today. It's a big canyon, spectacular canyon that can reach 50 meters of wall, and where we can see a lot of the fluvial process when we are observing the sedimentology of the outcrop. We know by the channel and by some boreholes that were made to water supply that the infilling of the alluvial fan has more or less 100 meters of sediment. Inside these main channels, we can observe some lava flows that infill old channels of the fan. We can find lava flows interbedded with sediments, or we can find tephra that we already dated with 200,000 years that can give us some geomorphic markers to understand the filling of this alluvial fan. We are doing surface mapping, but this was not easy at the beginning. There are a lot of inside surface. There are varnish and on the clasts connected with the wind and the hot temperatures that we have here, and with the basalt clast that we have And there is a color surface variability that is not easy to understand, and a lithological variability that is not well understood by imaging. Our questions were in the beginning if we had a single surface, different surface, 1, 2, 3, 4 lobes. So we started to draw the drainage pattern, and we made some surface profiles across the fan. The drainage pattern gave us very good results. Unfortunately, we didn't do this at the beginning. But when we did the drainage pattern, we realized that the lobes were quite distinguishable and quite easy to see. Our surface profiles were done to understand these lobes and to understand this organization of the surface. And we saw that with the surface profiles, the distinct lobes appeared. After that, we started to date the surface of the fan with cosmogenics. We collect samples from basalt blocks in the surface of the fan. Where we had a lot of careful to get a good sample from a boulder that was not moved. We take a lot of time to select each boulder where we pick up the sample. We want to be sure that the boulder was not moved and it was sufficiently buried on the surface to guarantee that the result could be good. Here in this map, we have the two campaigns that we made for collecting samples. The red dots represent the first campaign when we didn't have the drainage pattern yet, and we made along the sampling campaign along the main channel. And the second campaign is represented by the dark dots, and we plan in another way to get dates from each lobe. We only have dates from the first campaign, but the results that we have allow us to say that we have a wide range of dates since 10,000 till 160,000, and they are distributed along the fan. We have already tephra dated, and what we know of this distribution and what we can say about this distribution and the dates that we have. We have a recent or younger fan here. We have the older dates are among here, and on the bottom we have an intermediate date. Well, we can saw with these dates, we can say that we have a process of prograde and retrograde, like this older and this younger. We can devise some low switching from these dates, and that we have process of aggradation and excision, because we know that the active lobe, the active fan that we have on the bottom is younger than this one. And now relating this with a general view of this part of Africa. Well, we know that Africa experimented the African humid periods that we know that were more wet, and it was connected with what is so-called the Green Sahara, with rivers and lakes, and more presence of water in the system. And plotting the age that we had from the surface of our fan, we see that most part of these dates are connected with some African humid periods, which and this correspondence give us some intuition that alluvial fans can be connected with more presence of water in the system, and they are a climate geomorphic indicator of the change on climate on these areas. What we are doing now? We are doing drone mapping to understand better the surface of the fans. We are conducting studies to measure paleohydrology, namely calculate peak discharge using a method that is connected with the maximum boulder size. And what I can conclude for our research? Well, from the Geomorphic Index, we can conclude that rock strength, base level, and the volcanic edifice substructure, they are good records of the volcanic island erosion, and they are factors that influence this erosion and can give us a real state of the stage of erosion of each island. About the alluvial fans and the dating, we can say that these two islands at least have the landscape is sensitivity to African humid periods. We have a scale potential because we have huge landforms and well-developed landforms. Since we have a pile of sediments with a lot of thickness, we think we have a good temporal potential. And since they are close to Africa and the Sahara, they have a geographical potential to continue this research. And that's all. And thank you to all.